we have to go through with inference and statistics.
Okay. So yeah, so partly that is correct. Okay. So what we need to do is uh, we started stats with, with this, that there is a population, and from population we extract a sample. Okay. Now
Huh.
what happen is, from a population we can extract multiple samples. Okay. And
Okay.
when we get a random sample, okay, and we get a random statistic from that sample, for example a mean, or maybe a variance or anything. Okay. So I cannot be sure that this is a good representative of my population mean mu. Okay. So to prove this, that this x bar result, okay, is not only a random result, but it is a significant result which I can use, or which can help me in concluding something about the population behavior. Okay. So
Okay. Okay.
with inferential test we test these things. Okay. So z test is a tool for that, t test is a tool for that. And in the last class we also went through some assumptions, that when we will be using z test, when we will be using t test. Okay.
Yes. Yes.
So now let's look at these code. So every concept, everything is same. Okay. But the approach is different. Okay. So now we are using a software to do those things. Okay. Earlier we were just looking at some formulas and some diagrams. Okay. Now, so the idea is very simple. When you want to apply z test in our studio, okay, so by default you cannot use z test in our studio. Okay. You need to
Okay.
install this package, bsda. Bsda is a package, and just as I have already told you from the previous classes, that how you install a package. You go to this tab, and click on install, and then you will just write the name of the package that you want, and then install it. Okay. So
Okay.
once you have installed that, you will use the library command to load that package into the session. Okay. Once that is done, you can use this z test, and the idea is very simple. Okay. uh Very intuitive thing. Okay. uh Let me just first open this data. So this crystal wall is data, I guess. This is what I have shared in the classroom also. uh so from this data, I'll be using this data, and I'll be just applying these tests on this data. Okay. Though which test you will be applying on your data, okay, might vary from data to data. There are certain properties that a data set should follow. After that only you will be able to decide which test you will be applying to that data. Okay. But for just for the example purpose, I'll be just applying all the tests on the same data. Okay. Just to show you how to run these codes. Okay. And then I'll explain you the results that you will get after running these tests. Okay. But if you are doing a research, or if you are are involved in something where you are running these tests, okay, no matter what software you are using, no matter what tool you are using, okay, there are few conditions that you need to check before choosing what inferential test you will be applying on your data. Okay. So first thing is, you should be doing a normality check. Okay. For this we use Shapiro-Wilk test to check the normality of the data. Okay. And based on that we will see that whether we will be using a parametric test or a non-parametric test. First let's look into z test, which is a parametric test which is applied on normal data. Okay. Again I'm
Okay.
repeating this thing, that I'm just showing you these tests. Okay. But
Okay.
actually in a practically, when you are using these, first you will do the normality check, then you will decide the test. What I am doing is, I'll first explain you these parametric tests, then I'll tell you that how you gonna check the normality of your data, then I'll tell you that how you apply the non-parametric test. Okay. So
Okay.
this is what we'll be doing today. Okay. So z test. Okay. uh, so we have one sample test and we have two sample tests. Okay. For z test and t test, we have one sample test and two sample tests. Okay. Now in one sample test or a single sample test, what you have is, you usually have one sample with, you are comparing with already existing population mean. Okay. So for example, someone had studied the average salary of a data analyst in, let's say, 2020. Okay. And they concluded that, the population mean is something. Okay, they concluded that there is some X population mean. Okay, this is the mean salary of the data analyst as per that research that had happened in 2020. Okay, now in 2024, I am just looking at whether there is a change in this average salary of a data scientist, or it is same, or it has increased, decreased, or anything. Okay, so for that I will run a separate research. I will collect a separate sample. From that sample I will get a separate sample mean. Okay, and this sample mean will be something, let's say some y. Okay, and if this x is different from y, I will be using a z test. Okay, a one sample z test. Okay, which will help me in testing whether this, whether this mean, the sample mean, is significantly different from this population mean or not. Any question?
No, no.
Okay. Okay, so this is what we'll be doing. Okay, now let's look at a question, just to get idea, or let's just look at this data. Okay. Okay, so in this data, I have some performance scores. Okay, so these are some
Okay.
performance scores. Okay, so let's say there was a previous study regarding the same, whatever statistic they are measuring. Okay, and there
Okay.
was a certain performance scores, and the previous study concluded that on an average the performance score of the participants is, let's say, 80. Okay, now again I am running a separate research to confirm that whether the average performance score have remained the same, or it has significantly changed from what it was concluded earlier. Okay, so for that, assuming my distribution to be normal, okay, I'll be using a z test. Okay, for z test what we do is, this is how we run the formula for the z test in R. First is, if I want to, for first you have to run this library command for bsda. Okay, you will install bsda, then you will run the following object is mass no whatever. Okay, so first you will install the bsda, then you will run the bsda. Okay, with this library command, then you will write z dot test. Okay, and if bsda is installed and you have run this library command, then this z test will be appearing here, and the bsda will be in the bracket. Okay, so this z test. Okay, I want to run a z test, so I typed the z test, simple. Okay, now I have to define the data on which I'll be doing this thing. Okay, so uh I guess I have already renamed this data as this my S data. Okay, because this name is very long, so I've already renamed that. Okay, so I'm closing this. I'm using this my S data. Okay, so what I'll do is, first I'll define the data on which I want to run the Z test. So I have asked RStudio that I want to run the Z test. Now I want to run my Z test on this data set. Okay, now this is a single sample test. Okay, so I only need a single variable, that will be my performance score. So I'll use this dollar sign, and then I'll go to this performance score from this data. Okay, then next command will be sigma. Now this sigma for Z test, this sigma is the population standard deviation. Okay, so
Okay.
assumption for Z test is that the population standard deviation is known. Okay, so the formula will also need that. So let's assume it is 2. Okay, it is a made up example, so uh, I'm just showing an example, so maybe it could be different, but I have not tested that, so I'm just using 2 as an example. Okay, now once you have this sigma x, okay, that is your standard deviation, then you will also give it the population mean with which you want to compare your variable. Okay, so my population mean was 80 according to my example. Okay, so I'm writing 80, 80, oh sorry, 80. Okay, so the idea is, first you will call that test you want to run, then you will, with this x, you will define the data set on which you want to run the test. Then you will give the sigma x, which is your standard deviation, because it is needed for the z formula, and then mu, which is also needed for the z formula, so you want to define it. Okay.
Okay.
Then again comma. Okay. Now see, there is something called a two tail test, and then there is something called one tail test. Okay. So if you are testing the hypothesis and it is of the form x bar is equal to mu, okay, then this is a two tail test. Okay, it could be so this is my null hypothesis and this is my alternative hypothesis in this case. So either it is same as the population mu or it is different from the population mu. It can be more or less anything. Okay, if you are running a two-sided alternative hypothesis, okay, then you need not to define anything, then you need not to define alternative hypothesis separately. Okay, but if it is a one tail test, that is, if you are trying to see that whether the sample mean is more than mu, or you want to see whether sample mean is less than mu, then you have to define the alternative hypothesis with this command, which is just add a comma and then write alternative. Okay, and equal to sign.
Okay.
In quotes you have to define this less or more. Okay.
Okay.
Okay. Now, I guess I have already told this, but let me just repeat it. That if you forget, you know, that what command you need to put next in any code, okay, you can just put your cursor, this blinking cursor, inside the bracket of these code, and then click on tab. Okay, and should give you a result. Let me see why it is not giving me any result. Okay, so I didn't put a comma there, so it was not able to read what I wanted. So, you know, after comma, I want to add what. So if I want to define my alternative hypothesis, this is the command that I need to add, and then it also give you that what I need to write. So if it is more than, I need to write this greater in these codes. If it is less, then I will do this less. Okay. If it is two-sided, you
Okay.
can write two-sided, but if you are not writing anything, it is considered as two-sided. Clear?
Yes.
Any question till how this code is formed?
Uh, I do not understand with alternative hypothesis. Like when our main hypothesis is rejected, then we consider.
So uh, if your null hypothesis will always be what is the existing, belief. Okay.
Acha, yes. Okay.
Alternative will be either this, like, the sample
Uh-huh,
mean is
uh-huh,
not equal to population.
uh-huh.
Okay.
Right.
In this case, you need not to define alternative, this line, you need not to write this. Okay.
Okay.
But
Okay.
if your alternative hypothesis is either that your sample mean is more than your
Acha.
population mean, or your sample
Oh,
mean is
oh,
less than population mean, then you have to
right.
write this alternative is equal to, in quotes you will write greater or less, depending on whether it is greater or less.
Okay.
Clear?
Okay.
Clear?
Yes. Yes. Clear.
Okay.
Clear.
Okay. So this is how we put these commands. Okay. Now when I'll run this, okay, I will get, so in control enter. Okay. To run the command, I'll type this control enter. Okay. Then I will get the results. So these are the results. See, this is my z value. Okay. This is
Okay.
my p value. Okay.
Okay.
And this, so if you are not defining any confidence interval, it is always at 95% confidence interval. Okay, I'll tell you how you define this confidence interval. Okay, now this range, okay, this range is the interval estimate of this z value. Okay, what this range means is that my mu, that is my actual population mean, okay, or the real mean of the data, what we say the population mean, okay, will be somewhere within this range. This is called interval estimate of my population mean. Okay, so it is written a confidence interval. So interval is this from 66.17 something to 67.92 something. Clear?
Yes.
Okay. Okay. Now it is also given the sample mean of my data, that is the sample that I'm using, which is this data. Okay, the sample mean of this, it is giving me the sample mean of this. So this mean is this mean of this data, just the sample. Okay,
Okay.
clear? Okay.
Yes.
Now see, in the theory thing, okay, we talked about confidence level, we talked about significance level. Okay, so this
Okay.
95% is my confidence level, which means that I am 95% sure, okay, that if I pick any sample from my population, so I already told you na, that we can take multiple samples out of the population. Okay, so this
Okay.
95% confidence interval means that if I take any sample from my population, okay, there are 95% chances that my sample will lie, the value of mean will lie in this range. Okay, so I am
Okay.
95% confident that the value of my mean will lie within this range that is here. Okay, okay,
Okay.
but I am 95% sure, so there are 5% chances, you can say, of that the sample mean will be different from what I'm getting. Okay.
Hmm. Hmm.
Okay, so
Okay.
either you use a z table, okay, and then you will use that table to see if this z value is within your acceptable range, okay, or not. Okay, but in this software we get something called p value, which is that probability value, the probability, the chances of that error. Okay, now the rule with this p value, as I've already told you, since we are measuring this at 95% confidence, okay, we have a
Okay.
significance level or the alpha level of 0.05. Okay, if you are confused with any of these terms, you can look back to that theory video. Okay, we have discussed the alpha level, we have discussed the significance.
Uh-huh.
Okay,
Hmm. Hmm. Hmm.
we just refer
Okay.
that. Okay, okay, so uh, since my confidence level is 95%, my significance level is 0.05. Okay, now the thing with this p value is that if this p value, okay, is more than this significance level or alpha level, whatever that alpha is, okay, then you will accept the null hypothesis. Okay,
Yes.
that my mu is equal to 80, or my x bar is equal to 80, which is null hypothesis in my case. Okay,
Hmm.
but
Okay.
this is less than 0.05. Okay, then you will accept the alternative hypothesis. Clear?
Oh, yes.
Clear? Okay, so p value is that probability that, with what probability I can reduce the error. Okay, if that probability is less, then obviously you will reject your null hypothesis and accept the alternative hypothesis. Okay, if p is more than
Okay.
alpha, accept your null hypothesis. If it is less than alpha, reject your null hypothesis. And if nothing is given, we usually measure this thing, all these things at 95% confidence. So this is something default. Okay, so if you will look at the code, okay, I haven't feeded any confidence level or anything. Okay, automatically I'm getting this 95%. Okay, why we use this 95%? Because this is the most commonly used confidence level. Okay, and there is something called precision of the data. Okay, so for example, if I am I have this kind of curve. Okay, so the lesser the width of this curve, more precise is going to be my data or my result. Okay, so that's why we have this 95% confidence as a default one, though you can use any level that you want. Any question till now with this interpretation or anything, with p value, with this code, anything, any question?
No. No.
No? Okay,
No.
okay, so the formation of this code is clear to you.
Yes. Yes.
Okay, so whatever is needed to calculate your whatever test you are calculating, whatever values you need, you have to define those. So we need a sigma, which is an assumption that we know population sigma for z test. Okay, we need a mu. Okay, so that this is
Okay.
what we are getting. So basically the formula is something like you know x minus mu upon the standard deviation. Okay,
Yes. Yes.
so we are just putting these values, and this x is my data set that I'm using. Okay, so it automatically
Yes.
calculates everything and automatically gives me my sample mean also to compare with the population mean. Okay, clear?
Yes.
Okay, so I'll move to the t test. Okay,